Good morning, everyone. Thank you for joining us for our Engage session this month, featuring the Suomi National Polar Orbiting Partnership Mission, or Suomi NPP. Suomi NPP is the first satellite mission to address the challenge of acquiring a wide range of land, ocean, and atmospheric measurements for Earth system science while simultaneously preparing to address operational requirements for weather forecasting. The Engage series was created in order to engage the NASA and Goddard workforce in specific missions, projects, technologies. In this virtual environment, we have expanded that to the larger population outside of the workforce. A couple of housekeeping items to go through before we get started with the event. First, the chat feature has been enabled on the right-hand side of the screen in order for you to interact with the panel members to ask questions. There will be a question and answer session at the end of the discussion where we will get to as many questions as we can. Second, if you require closed captioning, please hover over the CC button at the bottom of the video. If closed captioning does not work at this time, the recording will be made available shortly after the event ends. Now, at this time, I would like to introduce each of our panel members and moderators that will be participating in the event today. Greg Mandt, the Joint Polar Satellite Systems Director, will be acting as moderator and participating in today's panel discussion. Mr. Mandt oversees the development, acquisition, integration, installation, and acceptance of major system elements for the JPSS satellites. Before coming to JPSS, he served as the System Program Director for the GOES-R program for 9 years, culminating in the successful launch of the GOES-16 satellite in November of 2016. Joining him for the discussion will be Heather Kilcoyne, JPSS Ground Segment Project Manager. Ms. Kilcoyne is responsible for the maintenance and sustainment of the acquisition, routing, and processing of the JPSS mission data from the receipt of the data at the polar ground stations through the production of the data products used by the National Weather Service and other mission partners and customers for weather forecasting and climate studies. James Gleason, the Suomi NPP project scientist and the JPSS program project scientist, will also be joining them. Dr. Gleason is the chief of the NASA Goddard Atmospheric Chemistry and Dynamics Laboratory, as well as serving as the project scientist for both NPP and JPSS. Finally, Dennis Furick, Vice President of Corporate Strategy and Development for USRA, will be serving as the moderator for the live Q&A from you, the audience, after the panel discussion. Now I would like to turn it over to Mr. Greg Mandt to kick off the panel discussion. Greg?
Thanks. It's an honor to be here and be able to share with the community a little bit of our history and a little bit of where we are and where we're going. As we look at SNPP, we realize we're coming up on its 10th birthday on orbit next week. So get the balloons and the party favors out because it's another great milestone. I guess as I get into the waning edge of my career, it's fun to look back at history here. And the SNP program, it's really important to really put it in the context, both in NASA as a space research agency and NOAA as the operational weather forecasting agency, of which space is a vital component. If we look at JPSS that I run, JPSS is really the collection of a lot of satellite data to bring to operational weather forecasting. We build some of our satellites in conjunction with NASA Goddard, such as SNPP and the JPSS series. But we also work with a lot of partners to bring those data sets in because in combination, low Earth orbiting satellites contribute 85% of the data that goes into the nation's weather forecast model. So we really are the backbone of your nation's forecasts. So it really touches every human in the nation every day. So it's a very, very important mission. So if we look back and at the history, you know, some people may ask, well, what is this Suomi, name on this satellite? Where'd that come from? And I did some research and a talk on him a number of years ago to the weather community, and he was a young boy from Finnish immigrants, grew up in the Iron Range, tough part of Minnesota, as a farm boy, very creative, and came to age in World War II, and he got put into the weather guys because he could make anything, being the good old farm boy, and he got into the weather business, and he actually designed and built the first. It was a flat panel radiometer that went on Explorer 7 in 1959, and it was really the first measurements of the Earth radiation budget from outer space, and it sort of inaugurated the observing of the climate from outer space. That whole science really started with Verne, and so that then grew into the massive Earth science program that we are all part of today. Now, from a NOAA perspective, that grew into the first weather satellite NASA built and launched in April of 1960, which was the TIROS program, which is basically just a imager. So the roots of that program were just to say pictures of clouds. And frankly, it was overwhelming. It was wonderful for the weather community because for the first time they saw what was going on a large scale. And one weather person was famously said, "We'll never be surprised by another hurricane again." Right? It was that kind of revolutionary thing. Now NASA kept improving that over the years. NOAA came in existence in the 1970s, so we created sort of an operational arm of the satellite from NASA, but still a very good partnership. In the 70s, we introduced a vertical sounder where we're actually measuring the atmosphere's temperature profiles. And interesting, NOAA doesn't have a lot of money to go develop new things, so we're depending on NASA to make those. But for the operational weather satellite series, from the 1970s, that basically stayed pretty stagnant through the 80s, through the 90s, and it was really behind the times. And it was NASA's investment in what was then, I recall, Mission Planet Earth and the Earth Observing System. Now you're still flying the Aquaterra satellites. That created a new instrumentation that got put on NPP and then moved into the operational data today. It's a revolutionary step for NOAA in terms of it. So great history here, great capability, and very vital to the nation. So Jim's been a very key component of all this. And, what's your thought on some of this instruments and this history and what we were able to accomplish bringing NPP online?
Well, I like to think of it as larger than NPP. I mean, it's been a continuous process of learning and partnership between NOAA and NASA. They started with TIROS. NASA flew the Nimbus series, which then led to POES, EOS, which then led to SNPP and JPSS. Each time, learning a little more, making the instruments a little more complicated, learning what we need to do from both a science perspective and then, onto an operational perspective. As you said, the first imagers were just black and white. We had the VHRR, which then turned to AVHRR, which were 5 and 6 channel imagers, which for the weather people were all of a sudden, it was more than just black and white. It was black and white and some temperature. And that was really the core of the system for years until EOS came around, and then everyone said, what can we do? And they flew MODIS, which was 36 channels, which was a lot of information. By the time VIIRS came around, it was like, do we need all 36? What's the right thing for NOAA? And they came to a pretty decent, set of VIIRS, which has got 22 channels, which then does clouds and fires and aerosols and sea surface temperature. Each time we add more information, more things that can be used by NOAA to make products and forecasts, or by scientists. Because by the time you've been flying instruments in space for 20 years, 30 years, 40 years, you can put all those data records together and you can figure out, is something changing? Because we have the measurements from space. And a key part of that, and one of sort of the differences between the our NASA research systems and the operational systems is the robustness of getting the data down to the ground. You know, it's not just making the measurements, it's how do we get them to be useful? And Heather's really, her project really does that really well.
Yeah, Heather, what are the kind of innovations that were brought in place this new generation of satellites for operations? How does that really data flow and all that?
Well, for NPP, we were kind of the precursor for our JPSS operational mission, but it really brought together, we're a multi-mission ground system, and we are all over the world. We have our receptor sites in Norway and Alaska, and we have 2 sites in Antarctica at McMurdo and Troll, along with support stations in White Sands, and then also in West Virginia we have equipment. So we're really, we say the sun never sets on the ground system. It's very expansive. To get all this data down, it's a polar orbiter, so we take the data at the poles, it's routed back to our facility in Suitland, where we take the raw data from the satellites and turn it into the data products that are used by forecasters and scientists. And it's really the first of its kind to be the full multi-mission satellite and then evolve that. The first part of this design, right, that was available for the first generation for NPP launch was there and started being developed in the early 2000s, right? And then we had the second generation come along with JPSS 1, now NOAA 20, and it has just grown, and technology has changed so rapidly over the past 20 years. We've been a little slower to adapt because we're operationally robust system, but we're able to bring in new technology as we can, like cloud for data processing. So we've done that in the past year. So it's been really fun to take this operationally robust system and be able to advance it where we can, while still maintaining the data products to enter into the forecasts at all times.
We're also doing some stuff with direct readout. I know that we've been working with the lab at Goddard as well as the University of Wisconsin. What do you got going on with the direct readout?
Well, direct readout started so originally, because all this was really envisioned right before the internet really existed and was as ever present as it is today. So we needed a way to get data, local data, to rural areas or places that were not easily accessible all over the world. So we have people that use our data all over the world. They get it at local antennas, they take the local data and use it. And now with the internet, that's becoming a little less necessary because they can just go to central sites and get the data and get global data. But it's been fascinating as that user community has grown. It's brought a lot of local weather information to remote areas so that they could get good quality forecasts for their customers.
Yeah, what's exciting to me about that is I know we bring the data down in the north and the south, as you mentioned, and that's really to reduce the latency because the numerical weather models really want this. And as they improve, they want it faster and faster, and they don't like any latency. So in the, before for this generation, we gave it to them once in orbit, about every 112 minute latency. And now they're screaming at us, and we've got it down to maybe 50 minutes, but they would like to see it instantaneous, so we actually have cobbled together, right? Some of the direct readout, we're actually taking all those data sets and over the internet, moving them to the numerical weather guys all over the world. It's a pretty exciting thing, but it shows that we always have to improve. We talk about where we've been, but there's a lot of improvements we do. And thinking back about since we support the numerical weather, those instruments are very, very critical. I remember when I was doing POSE, Jim, we had a microwave sounder unit that was a 3-channel feed horn driven by a belt to a little motor that spun it. And I think the last one I launched of those was on NOAA-J, and I think we didn't go any farther because NASA was embarrassed to build a belt-driven radiometer anymore in the 90s. So that took us to more advanced microwave sensors, and we're also doing filter wheel IR, and NPP introduced hyperspectral IR. So, any other thoughts in terms of these advancements in sounding instruments over the years and how critical they are today?
Right. Well, it's been a continuous measurement of you started with a few IR channels, they become incredibly useful. You add more, but then you get to limits of the technology of the time was limited in terms of the filters and the coolers and how fast you could do things. It really limited your data quality. With sort of the EOS program and that technology of that generation showed that you could build a spectrometer that instead of choosing channels and building an instrument and hoping you picked right, you could send down the complete infrared spectrum around the critical bands that provide the information. EOS did that. It was shown it was really useful, and NOAA said that's a great thing to do. We're gonna make. We want the infrared spectrum, and they went and took the idea of the infrared spectrum and went and built another kind of instrument that still gives us the same kind of data that is proved to be incredibly valuable. All of the weather centers now can pick the bands they want, and seems like every NWP center has their own particular favorite set of channels that they like to use, and it gives them the more importantly, it gives them room to expand, so that now you can do things where it's just not temperature and moisture sounding, it's temperature and moisture and trace gases and aerosols, and we're seeing people who are doing trace gases from the fires using hyperspectral infrared data, type of measurements that if you had told me you were going to do it when they were launched, I would have said, yeah, sure. So if you build a good instrument and you give smart people data, they will think of very creative ways to do things with. And then NOAA takes that information knowledge and then starts putting it out into products and services people can use. So the detection of aerosols turns into, hey, what's the air quality like from the fire? Where do we have to worry about it? What should the warnings be? And that's really where it gets to where it helps people and affects them every day. That, that colored map that you see of the air quality is in large part based on satellite data, based on the research stuff that people in now NASA and NOAA have done.
Very good. Another cool instrument, going back to Vern Sumi. He did the first. All he did is he painted a plate of metal white on one side and black on the other, and had it spin, and used that to calculate the outwelling radiation. Just simple solutions to it.
Right.
But we're flying now. The NPP is flying Ceres, right? NASA's Earth Radiation Budget Measurement. So I think that's the most continuous climate signal being measured from space, right? Is Earth radiation? It's the critical continuing.
Right. It answers it's a really good measurement. It takes, and this is one of these measurements that takes a long time because it's a very small signal. And recent data has shown, for those folks who don't know, what we're trying to balance is we know how much energy is coming into the sun, off the sun. That's carefully measured using a number of instruments in space. So the question is, how much energy is coming back from space? So you measure the reflected energy and the emitted infrared energy, and then you see if those numbers balance. And if there's more energy going in that's coming out, that means the planet's heating up. If there's more energy coming out than's going in, it means it's cooling off. And recent measurements have shown that, in fact, the planet has an excess radiation going in, and that amount of radiation is about equivalent to what we observe from space in sea surface temperature and sea surface rise. So our sense of how the planet is in balance or out of balance, and where is the energy going, is starting to be much better understood. Excellent. And that's all due to a very long data record. Yes.
And our final instrument on there is the ozone mapping system. I know NOAA has a federal mandate, a law that ever since the ozone hole was discovered of South Pole, to continuously monitor that, and so that continuity is provided by OMS. So an incredible legacy, an incredible history that has been in works for many decades. We're all just, little cogs in this long machine. It's exciting to be part of the Earth remote sensing. It's a critical area for NASA in exploring, and is a vital one for NOAA in terms of operationally supporting America. And we will continue our efforts. I know we've got this, so we've continued the SNPP instrumentation on J1, which is flying today as NOAA 20. We're building the next set of instruments, and we'll be basically replicas for numbers 2, 3, and 4. One thing NOAA does is we like to just buy a few things. Don't like to develop new things every time. A little bit different than NASA, but for
You get the bulk price.
That's the continuity aspect of it. So we're getting ready. We've got another mission in the barn. We got all the instruments on board. We're running it through environmental tests, so we're getting ready to launch that next year. But on an exciting front, we're actually looking forward for the next generation. What do we do now? One of the things, we're not just focused on one mission, build it and go for another mission. We sort of have a broader responsibility to keep this train moving, keep making the improvements, look for opportunities. And new space is really providing us, Elon Musk and SpaceX has done some creative things, and we're looking for ways to capture that, look for distributed architectures, and NASA's to really push the envelope of some of those with the Tempest program, and others where they're exploring some of these different smaller missions and its contributions. So we're trying to find the right line. The launch vehicle industry is really changing and giving us actually a much easier access to space. I had to buy an Atlas V for our J2 launch, which is way oversized for a low Earth orbit, because there really wasn't no medium class vehicles out there available. So now we're seeing medium and lower class that we can actually get much more responsive into space. So that it's exciting there. And really looking for, on the ground, Heather, for even improved latency, right? We're looking for how we can move this data around faster. Does the commercial marketplace provide us faster opportunities? What are you thinking on the commercial marketplace and opportunities? And I know you're doing some work with the commercial ground system providers.
We're looking at the current providers that are out there and what the new technology is bringing forward. Cloud computing has brought up a whole different world of how we can get data moved around even. So not being held to the same broadband communications, what can we do? Can we get better access to remote ground systems and put them at more places than just the poles to get a little bit of data and get it to us quicker and get it processed faster and get more data equals better forecasts. More frequent data equals better forecasts. So we are exploring with commercial data providers. We're seeing what we can do. So for the future, we have a great operational ground system now that takes not only data from our JPSS systems, but also EUMETSAT and JAXA, and we work with them in the whole international partnership. So we work with them. We can keep that going. But while we're able to do that, we can explore the way industry has just exploded over the past 10 years to see how we can use that at NOAA to do things more efficiently in the future so we can get more data and spend money elsewhere to get more instruments up to get more data and try to reduce the amount we spend on the ground, right?
Yeah, these are exciting times. I've briefed some sort of retired groups, in terms of where, like we call them the old weather farts, if you can use that term, but people who still are engaged in what's going on, and when they look at their career and where we are today and the exciting things and the technology and what more we can do from space, you can only imagine if someone like Vern Sumi was still alive, how excited he would be with the way technology is, the opportunities, and what more things we can measure and bring to bear to improve forecasts and life on Earth for everyone. So it is a very exciting missionary to be a part of. Certainly the Sumi Polar Orbiting Partnership is a key link in this. The partnership, NOAA and NASA have a long valued partner here. NOAA just relies almost totally on NASA for so much. But together we really produce a wonderful product for the nation. So excellent for where we are and where we're going. So I think that's about wraps up what our cumulative knowledge here. So why don't I turn over to Dennis and we can take any questions that anybody may have.
Great. Well, thanks, Greg and Jim and Heather for the great history lessons and insight. Some of the questions feel like they've been answered in time, so as in the discussion. But let me just kind of ask them again and see where we can go with them. So, in terms of the next generation instruments, talk to me about the changes from where we are now and what new technology is going to be looked for in the next generation of instruments for NOAA and the weather community.
I can start, Jim, maybe, and you can add color commentary, but the real workhorse for weather forecasting is obviously our sounder. So we really trying to get improved performance out of the microwave and infrared. A lot of it is driving down signal to noise, getting pure measurements, getting higher resolutions because the models continue to improve. One of the things we're really excited about is next generation is being able to have an instrument that can directly measure winds, because for weather forecasting, it's really temperature, moisture, and winds are the three variables that define how the atmosphere moves. And we directly measure temperature and moisture, but we haven't been able to do wind. So to explore ways to do that is an exciting prospect. The ocean color, the coast people, the people who are looking for managing our coastal areas, fisheries, and land ocean interface use the VIIRS instrument Jim mentioned for monitoring estuaries and such. They really have very demanding needs from resolution and refresh to really understand that dynamic, and space really provides the best area there. As Heather said, we're looking for cost reductions so that we can do more, basically. Those are my initial thoughts. Jim, you got any other ideas there?
Yeah, and we try to couple technology at the right level. There have been great advances in microwave integrated circuits. So where things were, AMSU and the POSE instruments had their microwave instruments in 3 separate instruments. ATMS took all of those on Suomi NPP, and JPSS took those 3 boxes and turned it into 1 box of about the same size. There's even more advances that will enable that to get even smaller. The smaller part means that there's the potential of putting them on smaller satellites, possibly, and then expanding the number. If you have a smaller satellite, you can put it on a smaller rocket. You can get it possibly more observing times. So not just at 130 on the backbone platform, but maybe we've shown that we want to add a few more because the sounding is critical. And if we have this smaller, less expensive, easy to access space, we can launch more of those and put more of that data into the forecast models. And that same technology is repeated in most of the instruments. The only caveat is, as you know, the more people want to do, the more and different types of data you want. And sometimes the instruments get bigger because people just want more.
Right. And another thing, Dennis, in that, other than the instruments, but as we mentioned, the latency is really one of the challenges. The models want everything instantaneously, so that's pretty hard to do with the construct we have today from a space to ground communication. But if people are familiar with what's OneWeb and what SpaceX is doing with Starlink, they're building these massive low Earth orbiting communications platform. While they're initially there to provide all of us really cool internet service through space with low latency, that's sort of where they are today. We're discussing with them. They're currently, all those satellites are interconnected with an RF link, so it's a relatively low data link. But SpaceX, for example, has said they're not going to launch any more RF connected satellites because they're installing optical interconnects, right? So now they're going to not only install optical interconnects, which dramatically increases the bandwidth communication between the satellites, but we're exploring how a satellite in a different orbital plane can communicate down into that low Earth orbiting network of it. And if we can work through that technological thing, we can have continuous communication between our remote sensing satellites into this orbiting network of communication satellites, who then can provide this instantaneous responsiveness. It's really an exciting thing. The Weather Service guys they're have some anticipation. I think they're saying they'll wait to show me. But again, it's another technology that is sort of a significant challenge to make this work. But I know that we're excited about the folks doing it and working. I know Goddard is also exploring a lot of optical stuff. We've been working with 450 and looking at how to apply some of these concepts. But it's another element of the future it's pretty exciting for our mission.
Would that include any onboard processing potentially, or is all the data too essential to get down raw?
We do some onboard processing, but you do want to get the full resolution that the users will want. You don't want to lose anything in that process.
Jim, in terms of kind of the technology path, now it's a very operational focus, clearly, but what type of R&D path into the kind of perhaps maybe it's on the ground side in terms of the big data and cloud type things as well, but what type of R&D input into kind of the weather satellite community are you focusing on these days?
Well, there's a pretty robust NASA development program going on. Greg mentioned the Tropics mission. There's the PACE mission for ocean color. There's a whole set of smaller CubeSat initiatives that people are doing. These are all things that demonstrate the potential. They don't promise to get all the data all the time right now. They just show, here's data. Does it have an impact? What is it really good for? Does the Tropics mission give us data to understand tropical cyclones better? When that's done and shown by a research mission, NOAA has the option of picking up that technology and putting it into an operational, robust system that Heather's works on and develops to make sure that the data gets there. Because that's the one thing the Weather Service wants, is they want their data before they make the forecast. Today's data, tomorrow doesn't really help the forecast, which is fine. That's fine for a research mission, not for a weather forecast mission.
Okay. Let me go a different direction. There was a nice shout out on the chat, a quick shout out to the OSPO and NSOF Ops and Engineering teams. First, who are they? What do they do? And talk to me about the team that is out there supporting operations in this community.
I'll take that. They make everything go. They fly the satellites. They make sure everything's up and going. They're there 24/7, making our ground system is working all the time. They are the operational branch of NESDIS. So at JPSS, we get to do the development, get things figured out, and then we hand it over to them, and they make it go, and they make sure that everything's running properly.
They make us all look good.
Oh yeah, every day. We try to give them things that don't break. That's our job.
Right. The operational infrastructure is so significant. I mean, when it comes not only just operating the satellites, but the whole data production teams, the user engagement teams that are out there working with various users to refine it. Because, one of the things, if I look at the way NASA does like the Earth sciences, they do decadal studies, they bring in the academic community, they find out what's the most important thing from a learning perspective. Well, NOAA isn't about necessarily learning science, but rather what are the practical day-to-day problems that people have that we can solve with our data. And the problem is those folks are not like PhDs, right? They're people who are emergency management people who get people out of the way and help when there's tornadoes, right? And if you ask them, well, what's the next observing data point you would like from space to help you with your job? They would like, could you buy me a cup of coffee, right? I mean, it's like, and so we work with those kind of communities, more practical, everyday Americans, to find out their problems. And then we do the assessment of what is it we can take from these data sets that really help solve their problem. And I think Jim highlighted one earlier with fire weather, right? I mean, yeah. we knew we could see, from the image behind you, Dennis, that's not only the nights of the light of lamps and lights, but rather fires actually show up on that. And we, with a 300-meter resolution imager, can see a lot of the forest fires that break out. In fact, sometimes we see them before they even know they're there, and so it's critical. The massive West Coast fires we've seen over the last few years, when we were working with them, they realized, the whole airspace for airplane control was affected by these massive clouds and all this. And so the forecast of that smoke and visibility became critical. And what the researchers found is they could take the radiative heat measured by our visible infrared imager, get a detailed heat signature from a fire, put that into the smoke model, and produce very accurate, improved smoke trail forecasts across the country, so that the airspace managers could actually plan for that and warn from it. So that's the kind of, you got to work with the users and really evolve these data sets and find new ways to actually use the data. It's
yeah. I'd like to, the map behind you, Dennis, has been used in the most clever ways. People, they take that map, and after there's a hurricane or tornado, there's a process now where they look at how are the lights different, how large is the power outage, how many areas are affected, and you do it at scale, so it's not just calling every individual power company. It's looking, yep, we can see the lights are out in these neighborhoods in Houston, and this is where we should be doing. And it's a very effective educational tool, illustrates to managers at all levels, the size of the problem and where things are.
Right. So from the emergency management communities find that incredibly valuable after disasters as a tool, and that gets into the White House, it gets into the senior level stuff, because it's a beautiful situational awareness of what's going on and what they need to do. And
it's something that was put up to measure clouds at night. And in fact, we actually measure dark neighborhoods. So it's clever people taking very good data and doing interesting things with it. And we just do that over and over again. And then when people like it, they want more. So fortunately, we can tell them they have another 20 years of day-night band to play with. So they'll be in good shape.
Yeah,
it's impressive, all the inputs that people just don't know is coming from these weather satellites. So another couple questions. Can you give any compelling examples of the data sets from different instruments on NPP, JPSS working together or complementing each other or complementing other satellites' data?
Okay. All right. So the obvious, of course, are the sounding, which basically does infrared and microwave to do a temperature sounding. Greg gave a really good example of, how the aerosols from VIIRS work in the weather model. We're doing air quality and pollution by combining the infrared data from CRIS and OMPS to basically get ozone in the troposphere. What else have we got? Lots of combinations of CRIS and VIIRS for understanding clouds and cloud properties using the thermal channels that are on CRIS that are not on VIIRS. Lots of multidisciplinary things within the sort of imager data, combined with other things. Lots of combinations of the series data for Earth radiation budget with VIIRS and CRISP for clouds and cloud types. That's really the sort of where people are going now, is how do we combine data sets?
I mentioned that JPSS was really a lot of partnerships in addition to what we build ourselves. So one of the products that's really manifests itself is in precipitation, right? So if you want to look at global precipitation, you know how hard of a problem that is? That, it is so variable, you can't look at it once a day and have any sense of what the precipitation patterns are. And so right now, the operational precipitation product has 18 different satellites, primarily microwave measurements, feeding into that. So that's why we've got our bigger challenge is we can't build everything, but how do we take advantage of all these satellites around the world that are contributing to a certain area and make the most of it to create products that are useful to
Great. No, all about the products. Let me go towards kind of from the science to the engineering side. This might be a smart aleck comment that was in here, but I'll read it and turn it into a question. Not a question, but a comment. You mentioned the old POES microwave sounders, belt-driven scanner. That belt failed on several satellites. I love being able to report that the instrument failed because the rubber band broke. Let's turn that into a question. What type of critical single point failures are you worried about? Have you seen? Talk to me about the engineering to make sure the current generation, doesn't have a rubber band break.
Yeah, that is a great comment. So it's we mentioned earlier it's hard to get humor in this type of virtual format, but that's a great one that I think we can all chuckle over. But a lot of it is in electronics right now. I mean, we really do a lot of work to build redundancy into these. In the old POES, I know we had a number of single point failures. In this generation of satellites, we've done a really good job of building redundancy across the systems. If I look at NPP, we took a hit. We don't know if it was a micrometeor or whatever, but it took out a third of the solar array. So again, it hit in a spot where it cut off the voltage from that panel. So we've only got 2 operational. So, but it was sufficient capacity such that we're still good. On the CRIS, we've gotten a couple of failures with some electronics boards for whatever reasons, and we've gone to redundant side. Then we had a failure in redundant side, a partial, so we're going back to the other side because that failure was less than this. So, we do have a number of small things, but we put a lot of energy into that. Now the problem is that's been very expensive, right? This generation of JPSS, meaning the instrumentation for NPP and all these JPSS and operations over a 20 to 30 year life cycle is about $18 billion. So as we said, in the next generation, we're exploring, well, you got to build that level of redundancy in, or can you build through smaller systems? Can you build resiliency on orbit as a trade-off, right? And then be responsive to replace it. Because actually, I think POES 15, I can't remember what year it was launched. It was launched in the 90s, is still operating, right? So that has lots of single point failures, and here it is, all these years later, still operating. So it's amazing, even when you have that, they can operate. And we're trying to explore what is the right amount of dollars to put into redundancy while still maintaining overall availability of these critical data sets.
Yeah, and I think it's.
Go ahead, Jim.
Yeah, no, and I think Greg brings up a good point. And to many, we were controlled by our availability of launch vehicles, how big they could be, what would happen. So we had a pretty limited our choices of access to space were much more limited. So we tended to build redundant, high-quality instruments that we're pretty sure were going to last a long time to make the investment in a large launch vehicle we had to buy worth it. That's all changing now. So I think we're all now looking at the new paradigm of, well, if we can get to space faster and cheaper, maybe we don't need to build triply redundant electronics because we have the ability to launch the next one faster and cheaper. So we're all just right now trying to understand, what does that mean? How do we do it, and how do we do it in the most cost-effective and risk-effective way?
So
because we feel like we're
NASA is developing, talk about the decadals, their Earth Systems Observatory, and the different kind of types of measurements there, as opposed to, platform design. Does that align, and does that kind of show the direction the next generation might draw from, given the kind of commercial technologies out there?
Simple answer, sure, yes. I'd like to highlight NOAA and NASA at the senior level recognize that this whole Earth science, it's really us two agencies, NOAA and NASA, who do that bulk of that work for the nation. And we have to be seen by our stakeholders in Congress and OMB, OSTP, as doing it in a very combined, coordinated way. And I know Steve Oltz and Thomas Zabrukin have initiated significant strategic efforts between the agencies to do that joint planning, to show, again, the creative side is the NASA side, right? That's the new science, that NOAA is just looking for what opportunities that you discover can we bring into the operational mission. So we're trying to do it at a higher level, a more complete look for opportunities. We've got a lot of joint initiatives. We mentioned PACE for ocean color. That's very exciting for NOAA. It's pushing the envelope for NASA, and we're going to take what we can from that to improve the operations. In cloud computing, in numerical prediction, in standards for metadata, we're working together to help make the whole Earth system more efficient, and to show people that NOAA and NASA are really together, pushing the envelope, doing things together, and that it's an enterprise the nation needs to invest in more, right? So I think it's a good sign for the leadership we have to build that collaboration and visibility, and we can only benefit from that in the long term.
Right. We do limited bits of that sort of combined thing now. The Sentinel-5P mission from ESA and EUMETSAT has come up with the most interesting methane and carbon gas emissions mapping, pipeline breaks in Russia. All of that data, the quality of that data is dependent on the fact that they're flying right behind Suomi NPP and using the VIIRS cloud and aerosol data in their retrievals. So they didn't bother to fly an imager on their instrument. We said, I can build a smaller single focus spacecraft, and we had some interesting negotiations about how you fly together, and they basically flew up right alongside, 5 minutes behind and off to the right. So they didn't need to fly their own imager. They just use ours. And that's been a great advance for, it essentially makes their methane data possible, is having VIIRS data. So people are being very creative about how they can use everything that's on orbit.
And that does, I mentioned earlier, but JPSS is really a family of systems that we use to support operations. And the Heather's ground system, is the ground system to support the data handling system to support JAXA in some of their Japanese instrumentation that is of interest to us. Very strong relationship with EUMETSAT in Europe. We take all their data passes down at McMurdo and move the data back to Europe. And then clearly on the sciences, Jim mentioned, there's tremendous collaboration in their sciences globally, really. So I think all of that is important for the mission and shows how we're just one little piece of a very, very important global effort.
Great. Let me ask another, I'll call it a technology question. We talked about some of the kind of the cloud big data technologies, but how about on the cyber side? Let me just ask bluntly, you know, like how do we keep hackers from taking control of our satellites and ground systems?
Go ahead, Heather.
Constant vigilance. Constant vigilance. Eternal vigilance. We have a strict security standard that we have to uphold to. We're evaluated every year. And our security team is very busy making sure that our system is secure.
Yeah, I always made a joke that we spent $2 billion on a ground system that is secure. We just hope that it can do something with the data.
Exactly. In balancing that between security and updating and doing it's a constant battle, but you can never let it go, right?
Right.
Dennis, an interesting anecdote is we went to Google and met with them because we were concerned of, well, can I really put this, like satellite operations, right? Can I put that in a cloud? And, you know, with all the security stuff we do, we're so afraid of that. And the Google technical guys looked at us like we were from Mars. And he goes, "Who are you? You're worried about hackers? We're Google. You think we don't have those? I got everybody on this planet trying to break into us." And we were sort of like embarrassed to think that we were so important. You know what I mean? So it's sort of an entertaining quip in terms of how seriously we take it. But it's a continuing challenge for everybody, I think.
Wow, good. Well, let me ask just generally, you know, the society's obviously focused on STEM, the next generation of talent. You know, how do you and how should we be getting the next generation involved in, you know, the space and weather satellite community? Are there any initiatives that you're tracking, following, or supporting in those areas, or the programs involved in?
We try to do that, especially us gray-haired people realize that we desperately need another generation. But as far as our program, we're heavily into the intern program. I think we had like 30 pre-COVID. I'm amazed that we actually had a number of people virtually interning over the last 2 years. So we really aggressively do that. But it's also to get them excited about their sciences and space. And interestingly enough, one of my messages to them is we're not all engineers, right? You know, we've got a great comm team. We got to create, you know, every aspect of education is really brought to bear on something, an enterprise this massive, right? And if you don't have to be the engineer, you can be the communicator. You can be the writer. You can help with scheduling, right, in the budget area, right? And we've had a lot of good internships. In fact, we even had former NASA Director Bolden's granddaughter a couple years ago, which was fun to have her. McKaylee did a outreach program for grade schools, and she got caricatures of all of us talking about this, and it was really fun. But again, that was an outreach to grade schools, right? To sort of introduce this in a very, very, very simple way to do all this. From a hiring thing, we've gone. I put in place a request primarily through our support contractors. NSAIC has done an incredible job with this, but we've brought in, I think, about a third of our hires are less than 10 years experience, you know, so it's a really an effort to get young folks who will be around a while involved. What we find though is we lose a good percentage of them because they're very mobile, right? So you need to be very active and keep a pipeline going. It's a little harder to get it into the Fed service, but we try to encourage a number of them to join the ranks, and we've had some success there. Except
Great.
we just lost one of our bright young ones, took a NASA position, so
kept them in the community. All good. All part of the family. Okay, rapid fire round here. Looking back at the last 10 years of Suomi NPP, happy birthday. What are each of your favorite applications or stories of the data being used in cool or valuable ways?
I got one.
Go ahead.
1 year after launch, we were coming up on the first anniversary of MPP being in orbit, and Hurricane Sandy hit, and they showed the impact that the MPP measurements on the forecast of Hurricane Sandy were quite significant, and that was just fruition of a lot of years of a lot of work, and just was amazing. And it's only gotten better since then, and the impact of the hurricane in particular forecast, and the daily forecast, how it's improved. I hear for the 7-day is now as accurate as a 3-day used to be, not just solely because of MPP, but modern forecasting and going from there. But the Hurricane Sandy really being influenced by MPP was a huge thing for me.
I'll leave Jim to last. I was over in Norway talking to the Norwegian Weather Service and how they apply it, and I had a laugh. They have a problem with Russian fishermen, trawlers, turning off their locator beacons, which violates international law, and disappearing into Norwegian fishing waters and doing their fishing and then leaving. And they're able, with the low light imagery that produced the picture behind you, Dennis, to actually track the lights of the trawlers to go after them.
And I would double down on that. The image behind you and the applications of that has been I think the single most interesting thing in terms of the breadth of use. We had a number of issues building the first VIIRs, and one of the questions was, do we really need this day-night band thing? And I was like, yes. Trust me. When you look at the world in a new way, you learn something. And that has been, that picture behind you, you can show it to anybody. The first thing they look for is their house, their neighborhood, the roads they drove on, and it's turned into something that you cannot, anything you can think of, someone's done something clever. They count gas flares and energy use globally. They count all sorts of things. So it's really been sort of the most useful things that you can show that to anybody and they know it. So much of our data is, what do those colors mean? You show that to someone and they get it right away. You can see the line of fishing boats on the Korean-Chinese border. It's practically a vertical line, So as Greg said, it's a great piece of data that we're really glad we hung on to, and it's proved its worth over and over again in applications that I had no idea anybody was really interested in.
Wow. Well, thanks for your great discussion, everybody, and happy birthday to NPP Sumo next week, and back to Bree to talk about the next sessions here. Thanks all. Fun discussion.
Thanks, Dennis. I want to take a second to thank all of you, our audience, for tuning in today, and especially our panel members and moderators for joining us for this special Engage session earlier than we normally have it. Please stay tuned on all of our social media pages and your email for next Engage session flyers, and I hope to see you all soon. Thank you.
Thank you.
Thanks.